Okay, so here we go. We're going to do an example. And in this case, we're going to use this function f of x is equal to e to the x. And we're going to show that the Maclaurin series for this function converges to this function on the interval of convergence. Okay, so here's what we're going to do. So first of all, we already determined the Maclaurin series for this in an earlier example. Okay, so we know that the Maclaurin series was given by this series. Oops. Okay, so that gives us the Maclaurin series. Okay, now to determine the interval of convergence, we use the ratio test. Okay, so we take the ratio, right? The absolute value of a sub n plus 1 over a sub n. Okay, and so this gives us when we do that, that's going to give us the absolute value of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. And when you simplify this, you're going to get the absolute value of x to the n plus 1 over the absolute value of x to the n. And we're going to get n factorial over n plus 1 factorial. Okay. And this will simplify too, because again, this n will cancel with n here, so we're going to end up with an absolute value of x in the numerator. So we're going to get the absolute value of x over, and then we're going to end up with n plus 1 in the denominator. So that's what we end up with. Okay, so now, the interval of convergence. Okay, so the limit, right? So this gives us this. So the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is equal to the limit as n approaches infinity of the absolute value of x over n plus 1. Well, this is going to go to 0 for all x in the real numbers. Okay? So therefore the series converges absolutely for all x, and thus the interval of convergence is negative infinity to positive infinity. Or in other words, all real numbers. Okay. So what does this show? Well, we're not done yet. Okay? Now, to show that the series converges to e to the x for all x, we need to use the fact that that the nth derivative of x is equal to e to the x for all n greater than or equal to 0. Right? The derivative of e to the x is e to the x for all derivatives. And e to the x is also an increasing function on the interval from negative infinity to infinity. So therefore, any real number b, the maximum value of e to the x for all values of the absolute value of x less than or equal to b is e to the b. Okay, so what does all that mean? Well, we know that for any derivative, right? So f to the nth derivative of x is equal to e to the x. And we also know, since this is an increasing function, that the bound, the upper bound for any interval is going to be the larger value. Okay? So for any real number b, the maximum value of e to the x for all values, so for example, if I say for any values of x, right, less than b, right, so for any real number b, well, that's going to happen, the maximum value for an increasing function is going to be at e to the b. Okay? So, that means our remainder, right? So that means the remainder, r of n of x, again, the absolute value of that, has to be less than what? It's going to be the f, well, in this case, it's just going to be e to the b, right? All right, because again, we're just using the fact that the nth derivative is always e to the x. So then all we're just going to do is fill it in with, this will be n factorial. No, I'm sorry, n plus 1 factorial. N plus 1 factorial, absolute value of x to the n plus 1. So let me erase this. Okay, so now, since we showed that this Maclaurin series converges for all x, by the divergence test, we know that the limit of that has to equal 0, right? So by the divergence test, we know that the limit of this has to be equal to 0. Or rather, hold on, let me start. Okay, we got this. Okay, let me get rid of this here. Okay, there we go. So we know that the limit as n approaches infinity of absolute value of x over n plus 1 factorial. Oh, hold on. n plus 1 over n plus 1 factorial. Okay, so again, by the divergence test, since we know this series converges for all values of x, then by the divergence test, we know that this has to equal 0. Remember that? Okay, so remember the divergence test was if this is not equal to 0, then this diverges. But remember, the converse, the implication was if this was based on the fact that all convergent series, the limit of the nth derivative, or not the nth derivative, but the limit of this would equal 0. Okay, so again, I'm just a little bit of review there. So we know that has to be true. Now, this is true for any real number x. Now, if we combine this fact with the squeeze theorem, then the result is that the limit of the remainder has to be 0. Okay, so we know this has to be less than this, which, oh, by the way, we can rewrite it as this, right? We can write it as e to the b times, so you can see it more, absolute value of x to the n plus 1 over n plus 1 factorial. Well, this is just this, right? So we know this limit is 0. So if we use this fact and the fact that r sub n of x has to be less than e to the b, right? Times this over n plus 1 factorial. And it also it has to be bigger than negative e to the b times the absolute value of x to the n plus 1 over the quantity n plus 1 factorial. Okay? So guess what? If I take the limit of all three pieces and use this fact here, then guess what? This is going to 0, and this is going to 0, which means the limit of this also has to be going to 0. That's the squeeze theorem. So we just showed that the limit as n approaches infinity of r sub n of x, the remainder, equals 0. And therefore, we have shown that the Maclaurin series for e to the x converges to e to the x for all x. And we're done.